Are you struggling to understand data structures? Don't worry, this video will make it simple and easy for you. What is a data structure? Data structures are a way of organizing and storing data so that it can be accessed and worked with efficiently. Data structures and algorithms are closely related, as they work together to solve problems effectively. Data structures help in the representation and organization of data, making it easier to manage. They also facilitate access and modification of data, allowing operations to be performed quickly and efficiently. Primitive data structures. These are the most basic or fundamental data structures. They act as the building blocks for data manipulation and contain simple, pure values. In Python, there are 4 main primitive data types: integers, which represent whole numbers; float, which represents decimal numbers; strings, which are used to store text; and boolean, which represents true or false value. Non-primitive data structure. Non-primitive data structures are more advanced types of data structures. They do not store just a single value, but instead store a collection of values in different formats. In traditional computer science, non-primitive data structures are divided into several types. These include arrays, lists, tuples, dictionaries, sets, and files. Non-primitive types data structures can be classified into 2 main types. First, simple data structures. These are built from primitive data types such as integers, floats, strings, and booleans. An example of a simple data structure is a linear list or an array. Next, complex data structures. These are formed by combining simple data structures in different ways to create more advanced structures. Complex data structures are of 2 types. Linear data structures, where elements are arranged in a single level or sequence. Examples include stack, queue, and linked list. And nonlinear data structures, where elements are arranged in multiple levels. Examples include tree and graph. Types of data structure. Data structures can be broadly classified into 2 main categories: simple and complex. Simple data structures include basic forms such as arrays or linear lists, which store data in a straightforward manner. Complex data structures are more advanced and are divided into 2 types: linear and nonlinear. Linear data structures store elements in a sequential order. Examples include stack, queue, and linked list. Nonlinear data structures store elements in a hierarchical or interconnected way. Examples include tree and graph. This classification helps us choose the right data structure based on the type of problem we want to solve. List. Lists in Python are used to store a collection of heterogeneous items, meaning they can contain different types of data. Lists are mutable, which means we can change their content without changing their identity. Each element in a list has an address, which is called an index. The index value starts from 0 and goes up to the last element. This is known as positive indexing. There is also negative indexing, which starts from -1, allowing us to access elements from the end of the list to the beginning. Common list manipulation. There are several common operations that we can perform on lists in Python. We can remove items from a list. We can sort a list or reverse its order. We can find the length of a list. We can also find the index value of a specific element in the list. And finally, we can count how many times a particular value appears in the list. Common functions. List. Python provides several built-in functions to work with lists efficiently. The append function adds a new element to the end of the list. The extend function adds elements from another list. The insert function adds an element at a specific index. The remove function deletes a particular element from the list. The pop function removes and returns an element from a given position. The clear function removes all elements from the list. The count function returns how many times a value appears in the list. The sort function arranges the elements in ascending order. The reverse function reverses the order of elements. The copy function creates a shallow copy of the list. And the length function returns the total number of elements in the list. Searching and sorting in list. In lists, two important operations are searching and sorting. Searching is used to find a specific element in a list. There are two common searching techniques, linear search and binary search. Sorting is used to arrange elements in a particular order. Two popular sorting methods are insertion sort and bubble sort. Binary search. In this program, we are implementing the binary search algorithm in Python. First, we define a function called binary search, which takes the array, the left index, the right index, and the element to be searched. We use a while loop that runs as long as the left index is less than or equal to the right index. Next, we calculate the middle index. We compare the middle element with the target value. If the middle element is equal to the target, we return the index. If the middle element is less than the target, we search in the right half by updating the left index. Otherwise, we search in the left half by updating the right index. If the element is not found, the function returns -1. Now, we define a sorted array with values 2, 3, 4, 10, and 40. We set the value of x as 10. Then we call the binary search function. If the result is not equal to -1, we print that the element is present at the given index. Otherwise, we print that the element is not present in the array. Binary search is efficient because it reduces the search space by half in each step. Binary search. In this example, we are implementing the binary search algorithm in Python. We define a function called binary search, which takes the array, the lower index, the upper index, and the element to be searched. We use a while loop that continues as long as the lower index is less than or equal to the upper index. Next, we calculate the middle index by adding the lower and upper index and dividing by 2. We then compare the middle element with the target value. If the middle element is equal to the target, we return the index. If the middle element is less than the target, we update the lower index to search in the right half. Otherwise, we update the upper index to search in the left half. If the element is not found, the function returns -1. Now, we define a sorted array with values 2, 3, 4, 10, 49, 50, 64, and 78. We set the value of x as 10. Then we call the binary search function. If the result is not equal to -1, we print that the element is present at the index. Otherwise, we print that the element is not present in the array. Binary search is efficient because it reduces the search space by half at each step. Let's take a look at bubble sorting, one of the simplest sorting algorithms. We start by printing the original list so we can see what we are working with. Then, we calculate the length of the list and store it in the variable n. Next comes the core of the algorithm, 2 loops. The outer loop runs n times, meaning we go through the list multiple passes. Inside that, the inner loop compares adjacent elements. Notice how it runs fewer times each pass. That's because the largest elements gradually bubble up to the end of the list, so we don't need to check them again. Now, here's the key part. If the current element is greater than the next one, we swap them. This process repeats until no more swaps are needed, and the list becomes fully sorted. That's why it's called bubble sort. Larger values rise to the top, just like bubbles in water. Now let's explore insertion sort, another simple and intuitive sorting algorithm. We begin by printing the original list and finding its length. Unlike bubble sort, insertion sort starts from the second element and assumes the first element is already sorted. For each element, we store its value in a variable called key. Then we compare it with the elements before it. Using a while loop, we shift all elements that are greater than the key one position to the right. This creates space for the key to be inserted in its correct position. Once the correct spot is found, we place the key there. This process repeats for every element, gradually building a sorted portion of the list from left to right. After each pass, we print the updated list so we can see how it evolves step by step. That's insertion sort, simple, efficient for small datasets, and works the way you might sort cards in your hand. Let's now look at list comprehensions, a powerful and concise way to create lists in Python. A list comprehension is essentially a shortcut for writing a for loop in a single line. It allows you to generate lists more efficiently and with cleaner code. In the first example, we create a list called mylist using this expression, I multiplied by 4 for every I in the range from 1 to 5. This produces a new list where each number is scaled by 4. In the second example, we add a condition. Here, we generate a list of numbers from 1 to 100, but only include those that are even, that is, numbers divisible by 2. At the bottom, you can see the equivalent traditional for loop. It does the same thing but takes more lines of code. So, list comprehensions help make your programs shorter, more readable, and often faster, especially when working with lists.
Let's break down the general structure of a list comprehension. In a traditional loop, we iterate over a set of values, apply a condition if needed, and then produce an output. List comprehensions combine all of that into a single, compact line. The format is an output expression, followed by a loop, and then an optional condition for filtering. Now let's look at some examples. In the first example, we generate a list by squaring each number from 0 to 9. In the second example, we create a list of numbers from 1 to 19, but only include the even ones. In the third example, we work with a string, mathematics, and extract only the vowels from it. These examples show how flexible list comprehensions are. They can be used with numbers, conditions, and even strings, all in a clean and readable way. Let's go through some practical examples of list comprehensions. In the first example, we take a list of uppercase letters A, B, and C, and convert each one to lowercase using the lower method. In the second example, we work with a string, hello 12,345 world. Using a list comprehension, we extract only the digits by checking each character with is digit. Next, we define a function called double, which multiplies a number by 2. We then apply this function to numbers from 0 to 9, creating a new list of double values. In the fourth example, we use two loops inside a list comprehension. Here, each element from the first list is added to each element from the second list, producing all possible combinations of sums. Finally, we generate random numbers. First, using randint, we create a list of random integers between 10 and 99. Then, using uniform, we generate random decimal numbers in the same range and round them to 2 decimal places. These examples show how list comprehensions can handle transformations, filtering, function calls, nested loops, and even random data generation, all in a compact and readable way. Now let's look at conditional expressions inside list comprehensions. In the first example, we generate numbers from 2 to 8. For each number, we check a condition. If the number is less than 5, we keep it as it is. Otherwise, we multiply it by 2. This shows how we can apply an if-else condition directly within a list comprehension. In the second example, we create a list that labels numbers as ev or odd, meaning even or odd. For each number in the range 10 to 19, we check if it's divisible by 2. If it is, we label it as ev, otherwise odd. These examples demonstrate how list comprehensions can include both looping and decision-making in a single, compact line of code. Now let's understand the concept of merge sort through this problem. We are asked to create two lists, A and B first. We sort both lists individually in ascending order. Once both lists are sorted, the next step is to merge them into a third list, called C. But this isn't just a simple combination. The final list C must also remain in ascending order. To achieve this, we compare elements from both lists one by one, always selecting the smaller value and adding it to the new list. This process continues until all elements from both A and B are included. The key idea here is combining two already sorted lists efficiently to produce a single sorted list. This merging technique is a fundamental part of the merge sort algorithm and is widely used because of its efficiency and reliability. Let's walk through the implementation of merging two sorted lists. We begin by defining a function called mergeSort that takes two lists, A and B. First, we print the original list so we can see their initial values. Next, both lists are sorted individually using the built-in sort method. We then store the lengths of A and B in variables L1 and L2 and print the sorted lists. Now comes the merging step. We create an empty list C, which will store the final merged result. We also initialize two pointers, I and j, starting at 0. These help us track our position in lists A and B. Using a while loop, we compare elements from both lists. Whichever element is smaller gets added to list C, and the corresponding pointer is incremented. This continues until we reach the end of one of the lists. After that, we use two additional while loops to add any remaining elements from A or B into C. Finally, we print the merged list C, which is now fully sorted in ascending order. This demonstrates how two sorted lists can be efficiently combined into one, a key idea behind merge sort.
Now let's understand the concept of a nested list. A nested list is simply a list that contains another list as one of its elements. In this example, we first create list 1 with the values 1, 2, and 3. Then, we create list 2, which contains the values 10, 20, and list 1 itself. So here, list 1 becomes an element inside list 2. When we print list 2, the output is 10, 20, and another list 1, 2, 3. Now let's look at how indexing works. If we access list 2 at index 0, we get 10. If we access list 2 at index 1, we get 20. But notice this, list 2 at index 2 gives us the entire inner list. To go deeper, we use double indexing. For example, list 2 at index 2, index 0 gives us the first element of the inner list, which is 1. So, nested lists allow us to store and access data in multiple levels, making them very useful for representing complex data structures.
This is a two-dimensional list, also called a 2D list. Here, my list contains 3 rows and 3 columns, like a table. Each inner list represents a row. We access elements using two indices, row and column. For example, the first element is at index 0, 0, and the last at index 2, 2. So, 2D lists help organize data in a grid format.
This shows how to initialize a 2D list. First, we take input for rows and columns. Then, using nested loops, we collect values row by row. Each row is stored as a list and added to the main list. Finally, we print the complete 2D list. This code shows how to traverse a 2D list. We use two loops, the outer loop for rows and the inner loop for columns. Each element is printed one by one in row format. After each row, we move to the next line. This code finds the sum of all elements in a 2D list. We start with a variable s set to 0. Using nested loops, we go through each row and each element, adding values to s. Finally, we print the total sum. This code finds the product of all elements in a 2D list. We start with p as 1. Using nested loops, we multiply each element with p. Finally, we print the result. This code adds two 2D arrays. First, we input values for both arrays. Then, using nested loops, we add corresponding elements from A and B. Each result is stored in a new list. Finally, we print the sum 2D array.